Let's now talk about logarithm, especially about its definition and formulas. The logarithm of base a is the inverse function of the exponential function of base a. So if we would write this to be y, it would mean the same thing that a to power y is x. Many times you see the definition of a logarithm written in this way. We can use this expression to evaluate some logarithms. For example, what's the logarithm of base 2 of 8? We should find a number that 2 to that power gives 8. A suitable power is 3, so logarithm 2 of 8 is 3. What's the logarithm of base a of 1? We should find a power of a so that the result is 1. Suitable power is 0. What's the logarithm of base a of a? We are looking for a power of a so that the result would be a. The suitable power is 1. Logarithm a of a to power x. We are looking for a power of a so that the result would be a to power x. The power is simply x. We see that here the logarithm and the a cancel out. Similarly, we can study that. How about if we take a to power logarithm of x? Can we cancel out the things here to obtain x? Let's study this equation. Let's take a logarithm of base a on both sides. Because we can cancel out here, we can cancel out here, and we see that the equation what we wrote down is true. We saw the definition of a logarithm and some basic properties. Let's next think about what kind of number a should be and how is the graph of the function. Let's first consider the function a to power x. We want a to be positive because otherwise we could take a to be -1 and x to be 1/2, and we would get square roots of negative numbers. We don't want to have this, so we take a to be a positive number. Also, we don't want a to be 1, because if a would be equal to 1, our original function would just get values 1, and it would not be invertible. If in the definition of a logarithm we would set a to be equal to 1, we would get in the right hand side that 1 to power y is x. So the only value of x what we could consider would be 1. This is not very interesting, so let's remove this case. Also the values that a is between 0 and 1 are not really interesting. We could consider the logarithm of base 1/2 of x, let's say 4. We would have to find a power of 1/2 so that the result would be 4. Well, 1/2 is 2 to the power minus 1. And we could take the powers minus 1 on both sides. We would get that 2 to some power should be 1/4. We see that the suitable power is minus 2. Instead of this, it's more easy to consider the logarithm 2 of 4. What's the power of 2? That gives 4. That's simply 2. We can study this number by considering this number and putting a minus sign there. So actually all of these logarithms we can express in this way. So no need to have any numbers between 0 and 1. So we are left with these functions. For all of these functions the graphs look like this. The function will be an increasing function. And some special cases at 0 the function will get value 1, and at 1 the function will get the value a. Let's now draw a graph of the inverse function. Let's draw the line y is equal to x. The graph of the inverse function is a mirror image. So the graph of a logarithm looks like this. We see that the variable x can only be positive, and if we would denote the values by y, we see that y can have any value. So we can denote the function more completely. Logarithm of base a takes positive numbers to real numbers, and the definition is here.